We're making headway in our overview of the universe. We've now looked at the various denizens, planets, stars, galaxies and so on, and how they've spread about, uniformly on large scales, but lumpy on small scales. And we've also looked at the basic stuff from which they're made: atomic and dark matter, light and neutrinos, and dark energy. In this lecture, I want to give an overview of the history of the universe, starting with the Big Bang and ending way in the future. I'm afraid I'll be moving along at quite a clip, roughly 8 million years per second. But don't worry if you don't quite catch everything first time. I'll be returning to essentially every theme in later lectures. So let's get straight away started by postponing a key question to Lecture 7, which is, how do we measure the age of the universe? It turns out to be 13.7 billion years, plus or minus about 0.1 billion. Now, to humans, this is a huge span of time. It's 3 times the age of the Earth. It's 50,000 times older than Homo sapiens, and it's 1 million times older than all of recorded human history. It's difficult to conceive of such a span of time, but here's one approach that provides a human terrestrial perspective on cosmic history. At the top of a 4-story building sits the Big Bang, while at the bottom is the present time. Here you can see some key events and periods: the first stars, the first galaxies, the formation of the Earth, the emergence of simple and complex cells, the first multi-celled creatures, and so on. Now, to get to humans, you really need to zoom in on that lower part. The lowest 4 inches contains dinosaurs and mammals. The lowest 1 millimeter contains all of the genus Homo. The lowest 10 microns, that's the size of a human cell, contains all of recorded human history. And finally, the lowest 100 nanometers is a century of time, roughly a human lifespan. So we need this nested zoom to bring our own brief lives into the story. But in these lectures, we want to look at cosmic history not through human eyes, but in a sense through nature's eyes. And so we need to adopt a different perspective, one which zooms in on the beginning, not the end, for the simple reason that cosmic change occurs incredibly fast near the beginning. And after that, it slows down, so that by today, we live in an old, very slowly changing universe. So this diagram gives our new perspective by plotting time on an exponential axis, starting at the Big Bang. This bar represents a factor of 1,000 in time. We go from 1 million years to 1,000 years to 1 year, and continuing to a second, to 1,000th of a second, 1,000,000th of a second. And I've sort of broken the axis just before a microsecond and simply put the Big Bang at the end. Now, I've identified 10 important stages that we'll focus on. And if you can keep these 10 stages clear in your mind, it'll really help you follow the story as we encounter each of them in future lectures. Before we visit these 10 stages, I want to point out an important feature of cosmic change. Its pace starts out very frantic, but quickly slows down. The first 4 of our 10 stages occur in the first 10 minutes. The next 4 span 1 billion years. There seems to be this bizarre compression of activity at the beginning of time, and I want to show you why that is. Actually, the reason is pretty simple. The universe begins its life exceedingly dense and hot, but as it expands, its density and temperature both drop, initially very quickly, but then more slowly. This graph shows how the temperature drops as the universe expands. Mathematically, temperature is proportional to 1 over the cosmic size. So if we go backwards, When the universe was 10 times smaller, it was 10 times hotter. 100 times smaller, 100 times hotter. So you can see that as we approach the Big Bang and size goes to zero, temperature must zoom off to infinity very rapidly. Now, just as you'd expect for any substance, as temperature changes, the nature of the substance also changes. For example, steam into water, into ice. And it's like that with the universe. Early on, as the temperature is dropping rapidly, lots of changes are occurring in rapid succession. But later, as the temperature drops more slowly, so the changes occur more slowly. So with that introduction, let's now briefly go through these 10 important stages in cosmic history. So right at the beginning, the Big Bang's expansion is launched by a mechanism called inflation. If you like, inflation is the bang of the Big Bang. Now, as we'll see in lectures 30 to 33, it's thought that inflation begins with a seed region of a very special kind of dense vacuum. Rather like a very dense version of modern-day dark energy. Now, when space itself weighs something and makes gravity, a rather strange thing happens. Instead of gravity making the region collapse inwards, the downhill direction, if you like, is outwards. And so the region quite naturally falls outwards, expanding all by itself. Now, and since there is nothing to stop this expansion, it just keeps going, getting faster and faster exponentially. So we have a huge expanding region of dense vacuum. Now, for reasons which are not yet fully understood, this period of inflation abruptly ends, and the vacuum energy is converted to an immensely hot broth of every kind of subatomic particle. So the upshot of all this is that within a fraction of a nanosecond, the universe is launched as a rapidly expanding space filled with an exceedingly hot, dense gas. And it's from this gas that all the stars and galaxies will finally emerge. Back to our cosmic timeline, there are a number of fascinating things that happen in the first millisecond. That's 1,000th of a second. And we'll return to them all in lectures 27 through 29. But here I'll just hit the high points and group them all as stage 2. It's in these first moments that the forces of nature take on their current form. Now, these forces, strong, electromagnetism, weak, and gravity, affect everything we know. They bind protons into atomic nuclei and electrons to atoms. They drive nuclear and chemical reactions, and they hold planets and stars together. They are the agents of change and energy release in the universe. Now, unless you're familiar with modern particle physics, you may not realize that these 4 great forces of nature actually change their character in places of high temperature. Now, although these changes are imperceptible at millions or even billions of degrees, in the amazingly higher temperatures of the early universe, these forces were radically different. And in fact, at the earliest time, they were joined as a single force. So as this diagram shows, as the temperature dropped, the character of each force emerged separately. And so by about 1/10 of a nanosecond, as the temperature dropped below 1,000,000 billion, that's 10 to the 15 degrees, the final separation of the weak and electromagnetic force was complete. And from that moment onwards until today, those forces, which are so crucial to everything we know, have remained essentially unchanged. Now, in addition to the birth of the forces, these early moments also saw the birth of atomic matter, the stuff we're made from. Initially, the universe was filled with just quarks, photons, electrons, and neutrinos. It was way too hot for composite particles like protons. They were just bashed apart in the energy of all the collisions. But by about 10 microseconds, the temperature dropped sufficiently for quarks to remain bound together in groups of 3 to make protons, antiprotons, neutrons, and antineutrons. And if we adopt the sort of geological style naming convention, then as the quarks were converted into protons, the universe passed from what we call the quark era to the hadron era, where hadron is just a fancy term for protons and neutrons. Well, continuing on, at about 100 microseconds, the temperature dropped below another critical threshold when almost all the protons and neutrons were annihilated by antiprotons and antineutrons. Now, fortunately for us, not quite all the protons were destroyed. For reasons that are not yet understood, roughly 1 in every billion protons managed to survive. In a sense, you can date the birth of the protons and neutrons in the atoms of your body to this time, about 100 microseconds after the Big Bang. Okay, coming forward to a time of a few seconds, that's stage 3, the same thing happens to all the electrons and anti-electrons. There's a brief period of carnage when they almost all annihilate, but 1 in every billion electrons manages to survive, and these ultimately become the electrons we now find in the atoms that you and I are made of. Now, when the electrons and anti-electrons vanish, the dominant constituent of the universe becomes photons, light. Or at that time, because it was so hot, gamma rays. Going back to our naming terms, we've just left the lepton era, where lepton is for lightweight particles like electrons, and we've now entered the radiation era, where light is dominant. The radiation era lasts for nearly 60,000 years before handing over to the matter era. Now, at this point, you may be feeling a little uneasy. 1 second seems just too short a time for so much to happen. It seems almost absurd. The reason of this, the resolution of this worry is, I think, both simple and yet profound. It's difficult to think of things that happen in times much shorter than a second, for the simple reason that thinking itself, having a thought, takes about 1 second. But for a thought to occur, billions upon billions of things must happen. Let's return to our atom's eye view from last lecture, where we imagined atoms to be the size of marbles. So with that perspective, our brain is twice the size of the Earth, and neurons are thousands of miles long. To an atomic electron whose single orbit feels like 1 second, a human thought takes almost 30 million years to unfold. Stated poetically, nature's thoughts occur enormously faster than ours. To nature, that first cosmic second feels like an eternity, and in it there is time enough for many eras to pass. So let's continue with our story of the young universe, coming to stage 4, when the universe is about a minute old. Now, at that time, the conditions everywhere were rather similar to the centres of present-day stars. And this immediately raises a very interesting possibility. As you may know, it is at the centres of stars that temperatures are high enough to drive nuclear reactions. The sun shines, for example, because in its core, hydrogen is being converted into helium. So could something similar happen in the young universe? And the answer is yes, it does. As we'll see in Lecture 25, between 1 and 3 minutes after the Big Bang, conditions were just right for hydrogen fusion. And during that brief time, the universe underwent a stunningly powerful burst of nuclear fusion that converted a quarter of the cosmic hydrogen into helium. Now, when you do the calculations properly, it predicts a final product of 25% helium and 75% hydrogen. And amazingly, wherever you look in the universe, that is basically the composition you find. 25% helium and 75% hydrogen. This is a fabulous confirmation of our understanding of the 3-minute-old universe. Now, at this point, the pace really slows down. Not much happens for thousands upon thousands of years. The temperature steadily drops. After a year, it's down to 3 million degrees. After 10,000 years, it's down to 20,000 degrees. But this is still way too hot to form atoms, and so the gas is ionized. Just protons, photons, electrons, and helium nuclei zooming around, bashing into each other. As the universe expands, it also gets more dilute. For example, after about 10 years, the gas is then already thinner than the best man-made vacuums on Earth, about 100 billion times thinner than the air we breathe. Throughout this time, the primary quality of the universe is its enormous brightness. Photons of light outnumber protons and electrons 1 billion to 1. And it's not just that they're more numerous. If we divide their energy by c squared, the speed of light squared, we find that light actually weighs more than the matter. That's why this is called the radiation era. But remember from last lecture, as the universe expands, the density of radiation drops more rapidly than the density of matter. And so there comes a time around 60,000 years after the Big Bang when these two densities are equal. And from then on, matter's density is dominant, and we enter the matter era. Now, this transition from a universe dominated by radiation to a universe dominated by matter leads to a number of interesting things. But here, I'm going to use it to introduce the universe's expansion history, how the universe's size and expansion speed depend on time. See, as the universe expands, the gravity of all the matter and radiation pull back, causing the expansion to slow down. This graph shows, up the y-axis, the speed at which any two parts in the universe separate from each other relative to their separation speed today. As the universe expands, we move to the right from the left, and as usual, both axes are exponential. So you can see that the expansion speed was much faster in the past. And for most of cosmic history, the expansion speed has been slowing down. You can also see how the rate of slowdown, the deceleration, changes as we pass from the radiation era to the matter era. The line is steeper in the radiation era. Later on, as we move into the dark energy era, look how the expansion speed stops slowing down and starts speeding up. That's the famous accelerating expansion caused by dark energy. Here's a more well-known diagram that plots the actual separation between 2 points, rather than the separation speed. Again, starting at the Big Bang on the left, but this time with simple linear, not exponential axes. It's a classic graph that we'll meet a number of times in the course, and I'm calling it S of t. You can think of it as how the size of the universe, S, depends on time, t. And we'll look at why it has just the shape that it does in lectures 11 and 12. Okay, back to our timeline. Between stages 5 at 60,000 years and 6 at 400,000 years is a particularly beautiful time in the universe, because the temperature drops from 10,000 degrees, which is blue hot, to about 3,000 degrees, which is red hot. So the color of the light in the universe slips slowly through a rainbow sequence, from blue to green to yellow to orange to red. It's a really quite wonderful spectacle, and we'll look at that in more detail in lecture 14. Stage 6, at 400,000 years, occurs when the universe cools past another critical temperature, 3,000 degrees. Below this temperature, electrons can finally remain attached to protons to make atoms of hydrogen. It also brings about a remarkable transformation. The universe changes from being foggy to being transparent. It takes about 80,000 years, but from then on till today, the universe is transparent, which is, of course, why we can see distant galaxies. Now, it turns out that we actually witness this transition as the microwave background. Remember from lecture 2, the diagram of the universe we witness. Looking out in any direction, we see back in time, through the transparency of space, out to, up to, but not into this fog. The inside wall of this giant sphere is a wall of bright, glowing fog. Now, the light waves from this fog are stretched by cosmic expansion as they come to us, and they arrive as much longer microwaves. They're the famous microwave background. It gives us a direct picture of the universe when it was only 400,000 years old. Now, one of the most important qualities of the microwave background can be seen in this famous all-sky image. It is slightly patchy. And this brings us to the very important topic of lumpiness or roughness in the universe. For reasons we'll get to in lecture 32, the seeds of cosmic lumpiness go right back to inflation, when tiny variations in the density were spread throughout the expanding universe. Since the universe is now extremely lumpy, galaxies here and there with gaps in between them, a key question is, how did the initial slight lumpiness begin to grow? Obviously, we'll look at this in later lectures, but basically, lumpiness in dark matter was able to grow from 60,000 years onwards. But because of its fogginess, the proton and electron gas was held back, and its lumpiness couldn't grow until after 400,000 years, until after the fog had cleared. Now, during that interval, the conditions were right for a delightful phenomenon. The universe was filled with sound waves. The combination of a brilliant light trapped by a foggy gas behaves just like a lightweight, high-pressure gas. And when this gas permeates a clumpy distribution of dark matter, it responds by falling into and bouncing out of the clumps of dark matter. And these oscillations are sound waves. In a very real sense, the whole universe behaves like a multi-piped organ. In lectures 15 and 16, I'll be playing you the sound that these cosmic organ pipes made and showing you how cosmologists have used the nature of the sound to measure quite accurately many important properties of the universe. Well, continuing the story, after the fog clears, we enter a quieter, cooler period where the temperature steadily drops. It passes human body temperature after about 15 million years. At this point, although everywhere continues to expand, the expansion of slightly denser regions is a little bit slower than everywhere else, so the overall lumpiness continues to grow. After about 100 million years, stage 7 on our sequence, these denser regions finally halt their expansion, turn around and begin to collapse inwards. Once the collapse gets going, it proceeds quite rapidly, and by about 200 million years, sprinkled across the entire universe are collapsing pockets of dark matter and atomic matter. And it's in the centers of these that the universe's first stars are born. These first stars are huge by today's standards, and they shine like beacons. and they bring to a close that long 200 million year period of darkness. And for the first time, they light up the sky like thousands of brilliant jewels. Quite a wonderful transition. Now, these first stars have brief million-year lives, which end when the star dies in a gargantuan explosion. It's a supernova explosion. And the star's spilled guts spread out and carry newly made chemical elements out into the otherwise pristine environment. This process of element enrichment by successive generations of stars has continued even to the present time, so that by now, 2% roughly of all the atoms in galaxies are of elements heavier than the original hydrogen and helium. And I'll be telling the story of this, what's called stellar nucleosynthesis, in lectures 23 and 24. And of course, it's really the story of how the atoms that ended up in you and me were actually made. Okay, from this point onwards, a primary theme for the universe is the growth of ever larger structures in a hierarchical process, meaning small things gather to make bigger things, which in turn gather to make yet bigger things. So by stage 8 in our sequence, around 1 billion years, the first groups of stars have gathered to form galaxy building blocks. And finally, these are actually visible to us in the Hubble telescope's deepest images. This whole period of galaxy formation is really fabulously active compared to today's rather sedate universe. New stars are being born, massive stars are exploding. It's really quite a fabulous fireworks display. And it's captured, I think, quite nicely in this artist's impression. We're rapidly approaching today's universe, but let's pause about 5 billion years ago to notice several interesting things that I've loosely gathered together under stage 9. So about this time, galaxies began to mature into the kind that we see around us today, like this nice-looking spiral, which we're seeing at a look-back time of 5 billion years in the Hubble ultra-deep field. You can almost imagine this being the young Milky Way galaxy, and out in one of its spiral arms, a young sun and solar system are forming with a young Earth. It's also around this time that the large-scale web-like pattern of galaxies throughout the universe was becoming more well-defined, as galaxies flowed into the web strands and then down into places where they intersect. And where they intersect, the first huge clusters were forming, like the one here, containing thousands of galaxies zooming through a region a few million light-years across. Out on the cosmic scale, a rather interesting and very gentle transition was also occurring. Starting about 5 billion years ago, the universe's expansion speed started accelerating as the effects of dark energy began to be felt. Now, by the present time, not too much has changed, but let's extend this graph into the future, say to the next 50 billion years. You can really see the effect of dark energy driving an exponential expansion, such that the separation between galaxies doubles roughly every 10 billion years. So as the billions of years will go by, we will live in an ever lonelier universe. Our own galaxy will merge with a few neighbouring galaxies to make a huge ball of stars, but otherwise, all other galaxies will get further and further away from us. In fact, as each galaxy's expansion speed away from us passes through light speed, it'll become forever invisible to us. And no matter how powerful our telescopes might be, we'd still see none of them. So 100 billion years from now, our visible universe will contain only our galactic ball of stars. No Andromeda galaxy, no other visible galaxies, no visible microwave background. Everything will have been pushed beyond what is called an event horizon, a profoundly inscrutable boundary of invisibility. Now, an optimistic way to look at this potentially depressing future is that we are lucky to be alive relatively early in the life of the universe, when there is a rich cosmic history still visible to us. I've mentioned already how 20 years ago much of what's in these lectures wasn't known. Amusingly, 100 billion years from now, very little of what's in these lectures will be known either. As I said in the first lecture, now is an ideal time, both culturally and cosmically, to learn cosmology.